Hello, and welcome to today's Tuva Science Connections, where we're going to be thinking about thermal properties meeting spacecraft, getting at this HSPS 3-4, in which our students are being asked to plan and conduct an investigation to provide evidence that the transfer of thermal energy when two components of different temperatures are combined within a closed system results in a more uniform energy distribution among the components of the system, right? Getting at this second law of thermodynamics, which is great. But something that can be fun and helpful for our students is to help them build a better foundational understanding of why we care. Why is the second law of thermodynamics important? And we can do that by using some real world applications. So we could think about, okay, if we're designing a spacecraft to re-enter through the Earth's atmosphere, what kind of metals would we need to use? What would we need to consider about the properties of those different metals as it's coming back through the atmosphere, as it's being exposed to temperatures 3,500 degrees Fahrenheit or higher, as it's having all that friction coming through? So we could explore questions like what properties of metals relate to the second law of thermodynamics that we should consider when we're making a choice of what metal to use when designing our spacecraft, or like what would be an ideal metal based off these different properties that relate to the second law of thermodynamics. So let's dive in and take a look at this data set, the thermal properties of materials that Tuva has within their data set. Just a quick orientation of what we're looking at. The data come from Engineer's Edge. The data have 30 cases, and in this data set, each case is a specific type of metal, and there's 7 different attributes or 7 different properties, characteristics of those metals that we can look at across those 30 metals. And we can use that to make comparisons across metals, across different properties, how those things vary, things like that. So let's dive in and think about that first question we had of like, what properties are relevant when we're thinking about the second law of thermodynamics? Well, and when we're thinking about a spacecraft re-entering the atmosphere, well, it seems like we certainly want melting point, right? If like we're thinking about sort of what temperature at which different materials melt. So we'd want our melting point. We could think of, well, we're putting metal on the outside and it's getting exposed. So we need to understand the conductivity, the thermal conductivity of those materials and how that would interface between those two different temperatures, the metal and the outside world. Thermal expansion might be interesting, right? Because based on how high the temperature gets, what does that do to the other properties of the structure of the metal? So we could look at thermal expansion, things like that. Before we get there, let's take a look at what these different kinds of materials are that are included within this data set. So we can look at it here from the case card, diving into this attribute of metal type. Or we could look at it here from the table view and look down the column of material. Either way, this gives us a sort of a quick sense of, okay, there's 30 metals, but what are these metals? Like, what are we actually looking at? Some of these may be new, some of these you may be really familiar with. It actually doesn't really matter when answering this question. You don't need to know exactly what nichrome is to be able to look at its properties and think about whether or not we could use it for a spacecraft, right? Because that second piece is, okay, so we have our metals and we're thinking about, we have those different attributes that we were thinking about, thermal conductivity, melting point, and thermal expansion. How might those relate to figuring out what an ideal metal type would be? So first thing, let's just get a sense of like what the ranges are of these different variables that we have. And so we could look at, okay, so melting point goes from 6170 for tungsten all the way down to solder 50%. 50/50 is a melting point of 361 degrees Fahrenheit. Okay, so that's a pretty big range, right? Seems like we would want a metal that has a melting point that is higher than what it will experience when it comes back through our atmosphere. So maybe these things are sort of interesting, right? But it's not just melting point. We're also curious about thermal expansion, like what will happen as as this metal, as that heat transfer happens. So we could get a sense of kind of what's the range. Okay, so we've got, oh, well, tungsten's down here at a really low amount of thermal expansion, and whereas zinc is up here with a really high amount of thermal expansion, right? We're just doing some like initial exploration of our different variables to get a sense of like, what are the ranges and where are different metals at? We can now dive more deeply in and think about, okay, so if this is thermal conductivity, and as our spacecraft is coming back through the atmosphere, it's coming back in, we want to protect what is inside, right? We don't actually want to pick a material that has a high conductivity, because then lots of that heat energy would come into our spacecraft. So we're looking for something with a low amount of conductivity, but we also don't want it to change shape very much, right? So we could think about, okay, so here's the thermal expansion as compared to the thermal conductivity, and we're looking for something that's kind of hanging out down here in kind of the lower range. But right, there's that other variable that we need to look at. So we could look at melting point to get a sense. Okay, so melting point is obviously a numeric continuous variable. So what we're seeing is we can get a sense of how that varies from our dark blue to our light blue. But what we can also do is come in and we can think about, because we know we have that cutoff of 3,500 degrees Fahrenheit, we could think about, what if we made this, we sort of binned it into a categorical numerical variable? And what if we binned it by 500 increments? So, or increments of 500 degrees. So we're kind of getting this sense. So we've got a bunch here in a range where there are sort of lower temperatures than it would experience as it's coming in. That's when the melting point happens. That's not good, right? We don't want our metal melting on our spacecraft or on our astronauts. And then we have some temperatures that are above. And so we can get a sense of now sort of looking through where we're like, okay, so we want a general low conductivity, a general low thermal expansion, and we want it to not melt as it comes back through the atmosphere. Okay, well, maybe tungsten is a material that we could go with. And so we can explore and we can adapt and we can keep thinking about like, but are those the only attributes or only properties of metal that we're interested in? We could get a sense of, sort of then how does this vary by density, and where does tungsten fall out in terms of its density or things like that? We can continue to explore and think about these data in different ways, and thinking of this question of like, how could we design the spacecraft to think about what it is, like how we want to keep our astronauts safe. So through this activity, we can get a sense of what properties of metal relate to that second law of thermodynamics as it relates to this real world application. Like, what do we really care about to keep our astronauts safe? Conductivity, expansion, melting point, all of these are related and impacted as that heat energy is transferring. And with this activity, we can explore this idea of like, okay, so what would be an ideal material for us to choose for this application for creating a spacecraft? It seems that at least tungsten would be a good one to go with for the outside of that spacecraft. And then you could dive deeper into the engineering of like, okay, well, do we want tungsten all the way through, or do we want different metals layered on different components? And the activity actually has students design what they think the spacecraft should be made of. So this is obviously just one of many physical science activities and science connections that are available through Tuva. I encourage you to check out the science content library to find more related to this performance expectation, and as well as a variety of others and different topics. As always, feel free to reach out with any questions that you have about anything within Tuva, or for some advice. With that, have a great day and enjoy playing with the data.